Well, thank you. I guess I'll need to stand here because of the camera, but thank you very much for coming to the first talk here. This is the title. What we are doing, we are developing large-scale parallel codes. We are applying those codes. So what I'm first going to tell you relatively briefly about RMG, the real space multi-grid code that does DFT calculations. It has all kinds of capabilities. Well, first of all, it runs on Blue Waters, and there's a portal from which you can download it. It will also run on the next architecture, whatever it is. We don't know. We don't know who's going to get it. One can guess, but we'll make sure that it runs. It's part of a sustained Petaflops petascale performance benchmarks, which means that the vendor will make sure that it runs. Otherwise, it will not get it accepted. On version 3, it has CUDA managed memory. It supports Volta NVIDIA GPUs. It will do other things. Also new for version 3 is that soon, not immediately, we will be releasing the quantum transport module. We have been using it for years, but it had to be cleaned up, stabilized, etc. The code base had to be stabilized. That's all done now. So it's going to come out soon. The second part is actually going to be physics. We are going or chemistry. We are going to talk about atomically precise bottom-up, ground bottom-up graphene nanoribbons. It's not bottom-up graphene nanoribbons. And we are going to talk about molecular mechanism of growth, and also designing potential devices, and trying to see what characteristics they're going to have. So let's, okay, that's switch. First, a few view graphs about the real space multigrid method. It uses grids as a basis as opposed to plane waves. Plane waves are what dominantly physicists use. Grids are the dual equivalent of plane waves, but you can easily parallelize using domain decomposition. You can use multi-grid methods to accelerate convergence, often dramatically. So here, for example, you see the scaling on Crays with GPUs. You see that we reached a petaflop on less than 4,000 nodes. Clearly, with newer, bigger machines, the petaflop is going to be reached much sooner. We have a portal. We have many downloads. There's also Windows, Linux, Macintosh's binaries there, etc. Now, talking about newer GPUs, about a year ago or so, we got what was then a new NVIDIA GPU in the mail. We signed a non-disclosure agreement. They sent us this thing. Well, we already saw speed up by a factor of 5 on a single node with a single GPU. And you can see, well, this is rather capable GPUs. Now we have a Volta, 50% faster. We've done things a lot better, etc. Actually, we are going to release a new version, version 3, next week at the Electronic Structure Workshop, combined with a Penn State conference in theoretical chemistry. It's more than 100 people are going to be there. Next week, we'll be running a tutorial and releasing that version. We are often running tutorials at that workshop. What have there been design consideration and goals? We restructured the build process to improve code maintainability. We focus on next generation hardware features, templates, C++ are used throughout, OpenMP, MPI, threads, everything there. We are running at a fairly high fraction of peak. Because the bulk of computational power comes from GPUs, we have moved to CUDA managed memory as opposed to explicitly managed memory. That makes portability much easier. It requires for newer architectures for the GPUs, so Pascal or later. And here's the additional components to be released: nearly linearly scaled localized orbital code and electronic structure transport module. And I should stress that the formulation that we use with localized orbitals that are optimized variationally for the problem at hand results in a very compact orbital set, which, however, maintains full DFT accuracy. We are not talking approximate DFT calculations. We are not talking tight binding. We are talking full DFT accuracy. So now let's turn to, sorry, this is, electrons are slow here. This moves back. I press a button, nothing happens. I press it again. Anyway, here is the bottom-up synthesis of graphene nanoribbons, which has been a breakthrough in nanoribbon synthesis. Atomically precise, it's hard. Okay, very hard to grow. But if you start with the right precursors, you get polymerization, and then you have graphene GNR with no defects, period. That's a breakthrough that has been in 2010. We are looking here at the stages of growth together with experimentalists. This is when that molecule, which is not quite planar, fuses. Here's the graphitic nanoribbon. Here's the experiment. Here's the simulation from us. For both, you see that we agree with the final state, so that's nice, okay, but how does the synthesis occur? That's something that experiment cannot capture fully. And we are looking here at two steps. We assume it happens with two steps, cyclization and dehydrogenation, and we have experimental support that it does happen that way. So we're looking at the step first connecting here, and then this one is obvious, but here how it rotates, not extra hydrogens, is not obvious, and then hydrogens getting removed. That's what we model. Okay, I guess I'm in the way of transmission. The cyclization step, you see, does not occur in vacuum. It needs a metal substrate. And we are showing that on a substrate, indeed, the activation energy is much lower. It is lower because of the desorption of hydrogen that can move, desorb on a hydrogen substrate and go, instead of being removed in vacuum, which would mean breaking a bond and then putting it together, it will act. It can desorb to the surface. We have energy profiles, which I'm not going to show, but we are seeing both the catalytic effect of the metal and the hydrogen adsorption and dehydrogenation. For example, well, no, actually, this is a slightly different point. What is also seen experimentally, and that's key what we are going to talk about next, is that one can make the polymer on the substrate at a certain temperature, then keep it there without raising the temperature, and transition to graphene nanoribbon does not occur, but one can then use an STM tip to give a pulse to the polymer in a precisely that location, and then that's going to convert either fully to a nanoribbon or partially to a half nanoribbon, half polymer. And we figure out how it happens. It happens because of a charging effect, and there's the so-called arrhenium ion effect that that catalyzes the transformation and allows for this transition. That has already been published. You can read about that. But well, actually, let me go to this figure first, and then I'll go back. Sorry for the order. What we now have after that STM pulse, we have a graphene nanoribbon here. Those here things have been converted, and we have an intermediate state, half nanoribbon, half graphene. Oh, sorry, graphene is here, or graphene nanoribbon, and half polymer. Now it turns out that that has a lower band gap. Okay, here's this intermediate state that we call it intermediate. Here is the nanoribbon. Okay, this is an experimental picture. This is a theoretical picture. The gap is lower because of density functional theory does not give you a good band gap. Usually it underestimates it. But see, theory and experiment, apart from the size of a band gap, are in excellent agreement, and you can look at the local density of states and the DI/dV curves that show that everything is in order. So now we have a larger band gap structure, a lower band gap structure. Now let me go back to this picture here, and now you can think of a negative differential resistance, which has been, those concepts have been around for a while. So the idea here is that you have a quantum dot, you apply a bias, and the quantum dot has a localized level here, which, however, is not aligned with the Fermi level here, so there is a tunneling barrier. When you raise the voltage, these aligned, now you have resonant transmission, you transmit more energy, more electrons. Then you raise the voltage more, now this level is full, and here again you have a barrier so that the transition goes down. Okay, that's the concept, has been around to some, that's called resonant tunneling diode. The precursor there is the so-called Esaki diode, not quite the same concept, but similar. That has been around for a while. Turns out that these concepts get modified significantly at the nanoscale. Let me tell you how. Okay, so let's now, before I tell you how, let me tell you that we are going to try various nanoribbon devices connected to graphene leads just as seamless contacts, and we are going to try various structures here, various segments, see what works, what doesn't. So let's first try with a standard resonant tunneling diode device. So we here have the hybrid nanoribbon, nanoribbons barriers here, and what you see, you don't see negative differential resistance. What is the problem here? The problem is that the distance here is too low, so you get resonant transmission. Well, not resonant transmission, you get tunneling. You get enough of tunneling to completely wash out that effect. You make the segments longer. You get a slightly, you get a little bit better effect, but still not quite negative differential resistance. If you make it really long, you indeed get negative differential resistance. Okay, we have lengths, barrier segments with a length of 26 angstroms. Okay, so you're going 2.5 nanometers. That's quite a bit. You have a fairly long structure. Now you indeed get negative differential resistance. The distance is tiny, and the current is even worse. Okay, 100 of a nanoamp, you don't want devices working at that voltage. That's too close to noise. But at least things are working okay in a sense that here you have density of states alignment or level alignment. Here you have some more. You see that things aligned at the correct bias, and then you see that they misalign, but there's an issue here. Well, how about trying something else? We thought that we need to maintain the barriers small to have a good, to get a good tunneling, but we also see that we want to get a large tunneling distance, so the direct tunneling does not happen. So here we have not quite a periodic structure, but multi-segment, 5 segments. Let's see how it works. Well, it turns out that actually it works quite well. We get pronounced negative differential resistance. We get levels at zero bias. at bias of 0.38, levels aligned. They misaligned at a higher bias, but everything is working well. We have a peak-to-valley ratio of 3.1, which is very good. You aim at about greater than 2 or 3 is useful, actually. The currents stay close to 1 nanoamp, so it depends a little bit on the contact. And the differential conductance is fine. But what you see here is that at the nanoscale, we had to modify the design of the device because of direct tunneling, nanoscale effects, etc. And also, this is kind of different from what Tsu and Esaki many years ago suggested a superlattice type of a structure with classical alignment. They didn't talk about level alignments. They talked about tunneling through barriers. And that's kind of a classical structure. This is confined nano quantum structure, and it works. So we've actually submitted that. We'll see for publication. So just to summarize, we talked about the Petaflops capable open source electronic structure code called RMG. Has various features are listed here. You read faster than what I can tell you. It is going to run on the next generation system, no matter what it is and no matter where it is. The vendors had to make sure of it. There's an upcoming release of quantum transport module that can handle many actual tens of K atoms because it's linear scaling. Then we talked about understanding molecular growth of bottom-up graphene nanoribbons, ability to control locally the conversion, and fabrication. Actually, those structures have already been made. Measuring at those distances is another story. That's still in progress. Thank you very much for your attention.